Okay, let's go ahead and take a look at this today. So, limits, first of all, I think of them as the alphabet of calculus. And really, they're the building blocks of everything. Okay, so first of all, we're going to talk about finding a limit. Now, we need to be able to find a limit in a few different ways. Graphically, numerically, as a table, and then we need to also be able to find it symbolically. So let's just look at a nice, I'm looking at these pens, it looks like every one of them is, okay, so limit as x goes to 3 of x squared plus 2x plus 1. Okay, so we'll do that graphically first. And oops, that's the wrong one. Here we go. Need a graph. And let's go. I'm going to go, and a great thing to do is to store functions, and that's one of the things a grapher can really do for you. Okay. Let me, okay. Okay. Let's go. Because I don't really need the whole thing, and well, hold on. I want to go to 3. So we'll go down here like this and count by 1. Count by 5. So there we go. So one thing we're going to do is we're going to trace a graph. Oops, we want a graph trace, excuse me. Okay, 2.9. Okay. Now here, notice this precision is not good enough. So I'm going to come over here. I gotta love technology. Okay. All right. And I'm going to go ahead and add some place values. Okay. 2.99. Okay. 2.9999. And as you can see, as we come to 3 from the left, from below, it's approaching 16. Well, we can also come from above. 40/10. Okay. 4 and 100th. 4 and 1,000. Oops, wait, oh, 5. Oh, I wanted to do 3 and 1,000. Sorry, good point. Okay. Here, again, we're approaching 16. So graphically, we have to take those out. Okay. We would write this is 16 from the graph. We're reading a graph. The other way I could do this is making a table. Now in this table, what we're going to do is we are going to okay, so 2.9, 2.99, 2.999, 3, we're not going to allow ourselves to touch it yet. And now I'm going to go fill this in, and we're going to show that numerically that we have the same limit. So the way we're going to do that is we're going to go here. We're going to add a spreadsheet. Now, menu, insert, oh, no, I want to go to table, actually. Table, switch to table. I want F1. Okay, that's a good start. Menu, go to table. I want to edit the table settings. And I'm going to turn independent from auto to ask. And now what I can do is I can come over here and I can record these and we can do this. So this is doing it numerically.
But I kid the deceased whoremonger.
Okay, so now you can see what I've done is I've gone ahead, I've made this table. Now look, in shorthand, as x is going to 3 from below, my y values are going to 16. That's a one-sided limit. As x is going to 3 from the right, my y values are going to 16. As the two one-sided limits not only exist but are the same, we can numerically say the limit as x goes to 3 of f of x is 16. Now remember what this symbol means. It means x can't be 3. Excuse me. It could be as close to 3 as your little heart desires. So I could even have like 3 in a billion, 3 in a trillion, etc., etc., etc. Now, so you need to be able to find a limit graphically. You need to be able to find a limit numerically. And then we talked about algebra. So in this case, we're going to try direct substitution. And all direct substitution means is we substitute in. And 9 plus 6 plus 1 is 16. Notice now, leading into this, so now that we're doing it symbolically, now that we're doing it algebraically, we start with direct substitution. But we ran into some roadblocks. One of the roadblocks we ran into is something called an indeterminate form. So one of those, and the only one you know right now, is 0 over 0. So 0 over 0 is an indeterminate form, and it means do more algebra. So what are we going to do? We're going to do algebra. So let's think about some of the things that we could do. We could add fractions, get common denominators. We might have to, some people call it conjugating the numerator or conjugating the denominator. What it really is you're using a difference of squares approach so that you're going to have a squared minus b squared. Let's see if I can cook the books really quickly and come up with one of those. Let's see, how about the limit as x goes to 3. So let's try direct substitution. I think I might have done this right in my head. Let's see. 3 times 5 is 15. 15 and 1 is 16. The square root of 16. Oh, wait. No, just kidding. Is 4. No, this isn't going to work. No, because this will be 0 here, but this won't be 0 here. This is what happens when you make problems up off the top of your head. Okay, we'll do an easier one. The limit as x goes to 16 of the square root of x minus 4 all over x minus 16. This one will work. I'll do this one two different ways. As x goes to 16, this numerator goes to 4 minus 4, which is 0, and this is 16 minus 16, which is 0. So we have 0 over 0, which is an indeterminate form. So now we're going to look at kiddo number 1. Kiddo numero uno. Now that kid is going to say, hey, you know what? I'm going to look at this as a difference of squares. Because they say, you know, Mr. Isaac, 16 is 4 times 4. They're correct. So what they do is they say this is the square root of x plus 4. And this is the square root of x minus 4. And now, if you think about this, this says x is never 16. So this is never 0, and this is never 0. So we can simplify that out. And we have 1 over the square root of x plus 4. And now we do direct substitution, which is 1 over the square root of 16 plus 4, which is 1 over 4 plus 4, which is 1 over 8. Now, that's one way to do it. Now, some people don't think about factoring x minus 16 as a difference of squares. With practice, you can start to see things like that. Now, kiddo number 2. They say, you know, Mr. Isaac, I don't see that. What I see is this is like an A minus a B. Now, people call this conjugation. It really is a difference of squares approach. So they multiply by root x over plus 4 over itself. Now, when they do that, they get root x times root x is x. 4 times 4 is, oh, look, x minus 16. Holy simoleons, this is x minus 16 times 1 over root x plus 4. Now, notice I'm doing the algebra without the limits. So when I simplify this, I need to put a restriction here. And that restriction is x can never be 16. Why? Because if x is 16, I've just divided by 0. Okay? Now, let's put Humpty Dumpty back together again. So the limit as x goes to 16 of the square root of x minus 4 over x minus 16 is the limit as x goes to 16 of 1 over the square root of x plus 4. And we've already gone through this and we know it's 1/8. So now notice both those students looked at it a little differently and they were able to get the right answer. Now, and then we had some other ones too, like adding fractions and stuff like that. And maybe I'll circle back when we do derivatives and do some of those. Now I would like to talk about geometrically, when can we not have a limit? Well, now this is very important, and you need to understand this, because when we have derivatives, if we are not differentiable, since a derivative is a limit, it's going to fall to the same things. One, if the right and the left-handed limits exist, but they're different. And I'll just draw a quick example. Here we go. Here's the simplest example. And this is called a jump, a step, and it's a discontinuity. Okay. And, okay, so the limit as x goes to a from the left of my function does not equal the limit as x goes to a from the right of my function. Notice the two one-sided limits exist. That's the first one. And now some people call this an asymptotic discontinuity. And it's exactly what you think. When you look at the graph, you have a vertical asymptote. Okay? And I'll give you one where it's a vertical asymptote on both sides. Okay? And this is x equals, I'll call it a. So it's not continuous at x equals a. Now some people would say, hey, this function is continuous on its domain, but then you better realize how they're using those words. Now the third type is oscillation. So I guess the easiest way to look at it is, how about the sine of 1 over x? Because what's going to happen is, as you get closer to x, or to 0, excuse me, it starts to bounce faster and faster. In fact, let's look at that on a computer. So let's get this. Oops, there we go. Now, did you know on your Inspire, if you have an Inspire, I'm going to insert a new problem, and I'm going to look at a graph. And this graph is going to be the sine of 1 over x. Now, let me go ahead and do menu. Let me do zoom. Zoom in. You zoom in. See, the closer you get to 0, do you see how the function isn't approaching a value, but it is bouncing faster and faster and faster and faster? Whoa, but Mr. Isaac, maybe we shouldn't zoom in so much. Well, let's take a look at this. Oops, it's the wrong button. I want menu. I want to zoom out a little bit. Because I want to zoom out. Okay. But now notice your y values are going between -1 and 1. So what I'm going to do is we're going to add this. We're going to go to menu, table, switch to table, f of x. Menu, table, we want to edit the table settings. we want to change this from automatic to ask. I'm only going to worry about the one-sided limits because 1 over x is odd, the sine function is odd, and the composition of odd functions is odd. Okay, so let's see. 1/10, 100. Okay. Hey, Roxy, how are you? Oh, wait, hold on. I got an upset dog right here, okay? See how I'm getting closer to 0 and how it's now starting to bounce faster. Oops. And faster. 3, 4. Right? And faster. Now notice at 0 it's undefined. So those are the 3 ways that you cannot have a limit at a point, which means when we go to have derivatives, we're going to have one of those discontinuities. Now, if my memory is correct from there, we started talking about continuity of a function. Now, a function is continuous at a point. And continuity is based on a point-by-point definition. And you'll see math books write it like this. It's really a 3-step process for the beginner. Step 1, the function is defined. So when you evaluate it at that point of interest, you get a finite number. Step 2, the limit as x goes to a of f of x exists and is some finite number. And finally, the limit and the functional value are the same. Now from there, we started talking about there were times when we needed one-sided limits there. We couldn't just use the limit command. And that comes into play when you're dealing with piecewise functions. Now you need to remember a piecewise function has pieces. Okay, so let's look at a couple of examples. Okay, now what I'm thinking here is, and I'm hoping you're finding this helpful, we're going to look at f of x is the sine of pi x, how about pi 2 times x? And we want to show f is continuous. Okay, is f continuous at x equals 6? Okay, f of 6. Well, that's the sine. Half of 6 is 3 of 3 pi. That's 0. 0 is finite. We've taken care of the first box. Now the limit as x goes to 6 of f of x is, by direct substitution, that's the limit, as x goes to 6 of the sine of pi over 2x. Now we use direct substitution. Oops, excuse me. This is the sine of pi over 2 times 6, which is the sine of 3 pi. And the limit exists. There it is. And that just also happens to be f of 6. Therefore, f of x satisfies the definition of continuity at x equals 6. So f is continuous at 6. Okay. Then we looked at some of the applications of continuity. Of limits. The first is continuity at a point. From there, we talked about how do we extend this to intervals. And we used algebra there. And then we talked about vertical asymptotes, horizontal asymptotes. And then we started by going in and looking at rates of change. And then we led to what's called the derivative at a point. And then from there, we started to expand it. Now, I have not talked about the intermediate value theorem yet, and I should. The intermediate value theorem only needs one thing, one major idea, and that's continuity. So when we talk about the intermediate value theorem, it says this. If you have a function that is continuous on a closed interval, and the y values at the endpoints are different, because of continuity, the function takes on all values between those two y values at the endpoints. Okay. And we talked about how we were going to justify it. And I think that kind of wraps up just a quick look at continuity and at limits and all of that good stuff. And if I need to come back and visit this more often and visit this again, I'm willing to do that. so that you guys and gals can be successful.